Microservices System Design in Cloud-Native Applications. Introduction. Microservices system design is the process of designing applications as a group of small, independent services that work together. Cloud-native applications are applications designed to run in modern cloud environments using containers, Kubernetes, CI/CD, observability, automation, and scalable infrastructure. Software engineers often learn microservices system design to build scalable backend systems, cloud-native applications, distributed systems, event-driven platforms, high-availability APIs, independently deployable services, Kubernetes-based applications, resilient production systems. A common learning topic is, how can software engineers design microservices in cloud-native applications, step by step? This guide explains: check, microservices basics, cloud-native architecture, service decomposition, database per service, API gateway, service discovery, synchronous communication, asynchronous communication, event-driven architecture, Kubernetes deployment, observability, security, scaling, resilience, monitoring. Interview questions. This is one of the best practical guides for backend developers, full-stack developers, and cloud-native engineers learning microservices system design. Simple definition. Microservices architecture is an architecture style where one large application is split into small independent services. Simple idea. Big monolith application. Small independent services, user service, order service, payment service, inventory service, notification service. Each service owns a specific business capability. Example: order service handles orders, payment service handles payments, inventory service handles stock, notification service sends emails, SMS. Microservices help teams build systems that are scalable, independently deployable, easier to maintain, loosely coupled, cloud-friendly, team-owned, resilient, flexible for different technologies. Example: if payment traffic increases, scale only payment service. No need to scale the whole application. Monolith versus microservices. Feature: monolith microservices. Deployment: one big deployment, many small deployments. Scaling: scale whole app, scale individual services. Database: often shared, usually database per service. Team ownership: shared codebase, service ownership. Failure impact: can affect whole app, can be isolated. Complexity: lower initially, higher distributed complexity, best for small, simple apps, large, scalable systems. Simple rule. Start simple. Use microservices when team size, scale, or domain complexity justifies it. Cloud-native microservices architecture. Typical architecture: front-end, mobile app, API gateway, microservices, databases, cache, message broker, Kubernetes, monitoring plus logging plus tracing. Example: React front-end, API gateway, user service, order service, payment service, inventory service, notification service. PostgreSQL, Redis, Kafka. Kubernetes core cloud-native components. Component purpose container package app and dependencies. Docker build container image. Kubernetes deploy, scale, and manage containers. API gateway, entry point for clients. Service discovery, find services dynamically. Config map, external configuration. Secret, sensitive configuration. Ingress, external routing. Observability, logs, metrics, traces. CI/CD, automated build and deployment. Step 1. Understand business domain. Before designing microservices, understand the business. Example: e-commerce domain. Users, products, orders, payments, inventory, shipping, notifications, reviews, coupons. Do not start with technology first. Start with business capabilities, user flows, data ownership, transaction boundaries, team ownership, scalability needs. Step 2. Identify service boundaries. Service boundaries define where one service ends and another begins. Example: user service, registration, login profile, user preferences. Order service, create order, cancel order, order history, payment service, payment authorization, refund, payment status. Inventory service, stock reservation, stock release, stock update. Good service boundary. One service owns one business capability. Bad service boundary. One service owns random technical layers like controller service, repository service, DTO service. Step 3. Avoid technical microservices. Bad design. Controller service, business logic service, repository service, database service. This is not good microservice design. Better design. Order service, payment service, inventory service, shipping service. Microservices should be based on business capabilities, not technical layers. Step 4. Database per service. In microservices, each service should own its data. Example: user service means UserDB. Order service means OrderDB. Payment service means PaymentDB. Inventory service means InventoryDB. Why? Loose coupling, independent deployment, independent schema changes, service ownership, better domain isolation. Avoid all services directly sharing one database. Problem: tight coupling, schema conflicts, deployment dependency, hidden business logic, hard to scale independently. Step 5. Data ownership. Each service owns its data. Example: order service owns order data. Payment service owns payment data. Inventory service owns stock data. If order service needs payment status, bad. Order service directly reads payment database. Better. Order service calls payment API or consumes payment completed event. Rule: a service should not directly access another service's database. Step 6. API gateway. API gateway is a single entry point for clients. Architecture: frontend API gateway user service, order service, payment service. API gateway responsibilities: check routing, check authentication, check authorization, check rate limiting, check request logging, check TLS termination, check response aggregation, API version routing. Example: API users / means user service. API orders / means order service. API payments / means payment service. Step 7. Service-to-service communication. Microservices communicate using type examples: synchronous REST, gRPC, asynchronous, Kafka RabbitMQ, streaming Kafka Pulsar. Synchronous example: order service calls payment service API. Asynchronous example: order service publishes order created event. Payment service consumes event. Step 8. REST communication. REST is simple and common. Example: order service means get / API users user ID. Good for copy simple request response, copy direct lookup, copy user-facing APIs, synchronous validation. Risk: service dependency, timeout issues, cascading failure, slower response if many calls. Best practices: use timeouts, use retries carefully, use circuit breaker, use fallback, avoid long chains. Step 9. gRPC communication. gRPC is useful for internal service communication. Good for COGS, high performance, strongly typed contracts, internal APIs, low latency communication, streaming. Architecture: order service, gRPC, payment service. Use when key services need fast internal calls. Teams can manage protobuf contracts. Clients are mostly backend services. Step 10. Event-driven communication. Event-driven communication is very common in cloud-native microservices. Example: order created event, payment service, inventory service, notification service. Benefits: loose coupling, async processing, better scalability, independent consumers, retries, and buffering. Common tools: Kafka, CIK, RabbitMQ, Pulsar, AWS SNS SQS, Azure Service Bus, Google PubSub. Step 11. Design events properly. Good event. Event ID, EVT1001. Event type, order created. Event version 1. Correlation ID, core ABC. Occurred at 2026-06-06 T1000Z. Data, order ID, ORD101. User ID, USR501. Amount, 149.99. Currency, CAD. Good event names. Order created. Payment completed. Payment failed. Inventory reserved. Shipment created. User registered. Bad event names. Process order. Due payment. Send email. Events should describe facts that already happened. Step 12. Saga pattern. Microservices cannot easily use one database transaction across many services. Saga pattern helps manage distributed workflows. Example order saga. Create order. Process payment. Reserve inventory. Create shipment. If inventory fails. Inventory failed? Refund payment. Cancel order. Saga styles. Style, meaning. Choreography services. React to events. Orchestration. Central coordinator controls flow. Step 13. Choreography saga. Architecture. Order service publishes order created. Payment service consumes and publishes payment completed. Inventory service consumes and publishes inventory reserved. Shipping service consumes and publishes shipment created. Benefits. Loosely coupled. No central controller. Challenges. Cut harder to trace. Flow spread across services. Debugging can be harder. Step 14. Orchestration saga. Architecture. Order saga coordinator. Call payment service. Call inventory service. Call shipping service. Handle compensation. Benefits. Colleague. Central workflow visibility. Easier business flow control. Easier compensation logic. Challenges. Coordinator can become complex. More central dependency. Step 15. Transactional outbox pattern. Problem. Database save succeeds. Event publish fails. System becomes inconsistent. Solution. Save business data and event record in same database transaction. Background worker publishes event later. Architecture. Order service. Save order plus outbox event dash outbox publisher dash Kafka RabbitMQ. Why important? Prevents lost events. Improves reliability. Supports retries. Keeps database and broker consistent. Step 16. Idempotency. In distributed systems, messages can be delivered more than once. Idempotency means processing the same request event multiple times gives the same final result. Example problem. Payment completed event. Processed twice. Order marked paid twice, or duplicate notification sent. Fix. Store processed event ID. Ignore duplicate event. Best practice. Use idempotency keys. Store processed event IDs. Design safe operations. Make consumers duplicate safe. Step 17. Resilience design. Microservices fail in many ways. Service down, network timeout, database slow, message broker unavailable, third-party API failure, Kubernetes pod restart. Use resilience patterns. Pattern purpose timeout. Avoid waiting forever. Retry temporary failures, circuit breaker. Stop calling failing service. Bulkhead, isolate failures. Fallback, provide alternative response. Rate limit, protect service. Back pressure, control overload. Step 18, circuit breaker. Circuit breaker prevents repeated calls to a failing service. Flow. Service call fails many times. Circuit opens. Calls fail fast. After wait time, try again. Circuit closes if healthy. Use for payment provider, external API, slow dependency, unstable service. Java tools. Resilience 4J. Spring Cloud circuit breaker. Step 19. Timeout and retry. Always configure timeouts. Bad. Service waits forever for another service. Better. Service waits 2 seconds, then fails safely. Retry only for temporary failures. Good retry examples. Cap. Network timeout. Temporary 503. Broker unavailable. Bad retry examples. Validation error. Unauthorized error. Bad request. Duplicate request. Rule. Retry transient failures, not business failures. Step 20. Service discovery. In cloud-native systems, service locations change. Kubernetes solves this using services. Example. Order service.default.svc.cluster.local. Payment service.default.svc.cluster.local. Inside Kubernetes. Order service calls http://payment service 8080. Kubernetes service provides stable networking for changing pods. Step 21. Kubernetes deployment. Each microservice usually has deployment, service, config map, secret, ingress route, resource limits, probes. Example. Order service, deployment, service, config map, secret, horizontal pod autoscaler. Step 22. Readiness and liveness probes. Readiness probe. Can this pod receive traffic? Liveness probe. Is this pod alive? Example. Readiness probe, HTTP GET, path, actuator health readiness, port 8080. Liveness probe, HTTP GET, path, actuator health liveness, port 8080. Best practice. Readiness checks if service can accept traffic. Liveness checks if app is stuck. Do not make liveness too aggressive. Expose Spring Boot actuator health endpoints. Step 23. Configuration management. Use external configuration. Examples. Application.yml environment variables, config map secret vault, AWS secrets manager, Azure Key Vault, GCP secret manager. Do not hard code. X database passwords, X API keys, X JWT secrets, X cloud credentials. Use config map for non-sensitive config, config map for sensitive config, config map for production. Step 24. Observability. Observability means understanding system behavior from check, logs, metrics, traces. Architecture. Logs means ELK. Loki metrics means Prometheus plus Grafana. Traces means OpenTelemetry plus Jaeger Tempo. Monitor. Check. API latency. Check. Error rate. Request count. CPU memory. Check. Pod restarts. Check. Database latency. Check. Queue depth. Consumer lag. Check. Circuit breaker state. Step 25. Distributed tracing. Distributed tracing helps follow one request across services. Example. Front-end request. Trace ID equals ABC. API gateway, trace ID equals ABC. Order service, trace ID equals ABC. Payment service, trace ID equals ABC. Useful for check debugging slow requests. Check finding failing service. Check understanding service dependencies. Check production incident analysis. Use Cuck, OpenTelemetry, Jaeger, Grafana, Tempo, Zipkin. Step 26. Logging best practices. Good log. Correlation ID equals ABC 123. Order ID equals ORD 101. Status equals payment started. Duration MS equals 120. Bad log. Processing. Logs should include correlation ID, trace ID, business ID, service name, duration, error code, safe message. Never log X passwords, X access tokens, X credit card data, X private secrets. Step 27. Security design. Microservices security includes CERT, authentication, authorization, service-to-service security, JWT validation, MTLS, API gateway protection, secrets management, network policies, rate limiting, input validation, common pattern. Client, API gateway validates JWT. Service validates authorization. Service accesses allowed data only. Important. Front-end security is not enough. Backend services must enforce authorization. Step 28. Data consistency. Microservices often use eventual consistency. Example. Order created now. Payment completes later. Inventory reserves later. Order status updates eventually. This means system may be temporarily inconsistent, but becomes consistent after events complete. Design 4. Pending states, retry handling, compensation, status tracking, user-friendly messages. Example UI message. Your order is being processed. Step 29. API design. Each service should expose clear APIs. Example order service APIs. Post API orders. Get API orders. Egg ID. Get API orders with user ID 101. Post API orders with ID cancel. Good API design. Clear resource names. Proper status codes. Validation errors. Pagination. Versioning strategy. Consistent error format. Step 30. Deployment strategy. Cloud-native microservices use automated deployment. Common strategies. Strategy, meaning rolling update. Gradually replace old pods. Blue-green switch from old to new environment. Canary release to small percentage first. Feature flag, enable feature gradually. Recommended. Use rolling updates for normal releases. Use canary for risky changes. Use feature flags for business features. Example, system design, e-commerce platform services, user service, product service, cart service, order service, payment service, inventory service, shipping service, notification service, review service. Architecture, React front-end, API gateway, user service, product service, cart service, order service, payment service. Service, shipping service, notification service, PostgreSQL, Redis, Kafka, Kubernetes, Prometheus, plus Grafana, plus OpenTelemetry request flow, place order 1, user clicks place order 2. Frontend calls order service through API gateway 3. Order service creates order with status created 4. Order service publishes order created event 5. Payment service processes payment 6. Payment service publishes payment completed 7. Inventory service reserves stock 8. Shipping service creates shipment 9. Notification service sends confirmation 10. Order status becomes confirmed. Failure flow. Payment failed 1. Order created event published 2. Payment service tries payment 3. Payment fails 4. Payment service publishes payment failed. Order service marks order as payment failed 6. Notification service sends failure message, failure flow, inventory failed 1. Payment completed 2. Inventory reservation fails. Inventory service publishes inventory failed. Payment service refunds payment. Order service marks order it's canceled. Notification service sends cancellation message. Java/Spring Boot Cloud Native Stack. Recommended stack. C. Java 17 or 21. Spring Boot 3. Spring Web. Spring Data JPA. PostgreSQL. Redis, Kafka or RabbitMQ. Spring Security. Resilience 4J, OpenTelemetry, Micrometer, Docker, Kubernetes, Helm, GitHub Actions, Prometheus. Spring Boot Service Structure. Recommended package structure. Order service, controller, service, repository, entity, DTO, event, config, exception, security. Benefits. Clear layers, clear testing, clear maintenance, production-friendly. Example order service design. Order controller, order service, order repository, order database, order event publisher, Kafka RabbitMQ. Main responsibilities. Create order, cancel order, track order status, publish order events, consume payment inventory events, expose order APIs. API gateway design. Gateway routes. API users. / means user service. API products / means product service. API cart / means cart service. API orders / means order service. API payment / means payment service. Gateway responsibilities: authentication, routing, rate limiting, request logging, TLS, CORS, request size limits. Avoid putting too much business logic in the gateway. Database design. Recommended. User service means user DB. Product service means product DB. Order service means order DB. Payment service means payment DB. Inventory service means inventory DB. Avoid. All services directly share same tables. When data is needed across services. Copy. Use API calls. Use events. Create read model. Use CQRS if needed. CQRS pattern. CQRS means command query responsibility segregation. Simple idea. Write model handles updates. Read model handles queries. Example. Order service owns order rights. Order search read model stores denormalized order view. Useful when queries are complex. Data comes from many services. Read performance matters. Event-driven projections are needed. Service mesh. Service mesh helps manage service-to-service traffic. Common tools. Istio, Linkerd, Console. Service mesh can provide. Check, MTLS, traffic routing, retries, telemetry, circuit breaking, policy enforcement. Beginner note. Learn Kubernetes services first. Learn service mesh after core microservices basics. Scaling strategy. Scale based on cache, CPU usage, memory usage, request rate, queue depth, Kafka consumer lag, custom metrics. Kubernetes HPA, horizontal pod autoscaler, scales pods automatically. Example. Payment service traffic high. HPA increases replicas from 3 to 8 caching strategy. Use cache for check, product catalog, check, user sessions, check, frequently read data, check, API responses. Common tool. Redis. Cache problems. Stale data, cache invalidation, memory pressure, inconsistent reads. Best practice. Cache, read heavy data. Do not use cache as source of truth. Common beginner mistakes. 1. Creating too many services too early. Bad. Small app with 20 microservices. Better. Start with modular monolith. Split when boundaries and scaling needs are clear. 2. Sharing one database across services. Bad. All services read and write, same database. Better. Each service owns its database. 3. No observability. Microservices without logs, metrics, and traces are hard to debug. 4. Ignoring network failures. In microservices, network calls can fail. Always use check timeout, check retry, check circuit breaker, check fallback. 5. No idempotency. Duplicate messages can happen. Consumers must be duplicate safe. 6. No contract testing. Service changes can break other services. Use check API contract tests, check schema validation, check backward compatible changes. 7. Too much logic in API gateway. Gateway should route and protect, not own business workflows. 8. No deployment strategy. Deploying many services manually is risky. Use CI/CD. Best practices. Check. Design services around business capabilities. Keep services independently deployable. Use database per service. Avoid direct database sharing. Use API gateway for external entry. Use events for async workflows. Use REST gRPC for direct lookups. Use transactional outbox for reliable events. Idempotent. Use correlation IDs. Add timeouts and circuit breakers. Monitor logs, metrics, and traces. Use Kubernetes probes. Use config maps and secrets. Automate CI/CD. Use contract testing. Design for failure. Start simple before splitting too much. Microservices system design interview questions. 1. What is microservices architecture? Microservices architecture splits an application into small independent services, each responsible for a specific business capability. 2. Why use microservices? To improve scalability, independent deployment, team ownership, resilience, and flexibility. 3. What is database per service? Each service owns and manages its own database or schema, and does not directly share tables with other services. What is API gateway? API gateway is the entry point for clients and handles routing, authentication, rate limiting, and cross-cutting concerns. 5. REST versus event-driven communication. REST is synchronous request response. Event-driven communication is asynchronous and uses events through brokers like Kafka or RabbitMQ. 6. What is saga pattern? Saga manages distributed transactions across multiple services using events or orchestration with compensation steps. 7. What is transactional outbox? Transactional outbox saves business data and event data in the same database transaction, then publishes the event later. 8. What is idempotency? Idempotency means processing the same request or event multiple times safely without duplicate side effects. 9. What is service discovery? Service discovery lets services find each other dynamically, often through Kubernetes services in cloud-native systems. 10. What is distributed tracing? Distributed tracing follows one request across multiple services using trace IDs and spans. 11. What is eventual consistency? Eventual consistency means data may be temporarily inconsistent across services, but becomes consistent after events complete. 12. What is circuit breaker? Circuit breaker prevents repeated calls to failing services and helps avoid cascading failures. Microservices roadmap, beginner level. Learn, monolith versus microservices, service boundaries, REST APIs, database per service, API gateway, Docker basics. Build. 2. Service REST system, intermediate level. Learn. Check. Kafka RabbitMQ, event-driven architecture, Saga basics, service discovery, resilience patterns, Kubernetes deployment. Build. Order plus payment plus notification system, advanced level. Learn. Transactional outbox, CQRS, distributed tracing, service mesh, autoscaling, contract testing, production observability. Production-ready e-commerce microservices platform. 30-day learning plan, week 1. Fundamentals. Learn. Check microservices basics. Check monolith versus microservices. Check service boundaries. Check REST communication. Check database per service. Practice. Design simple user service and order service. Week 2. Cloud native deployment. Learn. Cookies, Docker, Kubernetes deployment, Kubernetes service, config map, secret, readiness liveness probes. Practice. Deploy 2 Spring Boot services to Kubernetes. Week 3. Event-driven design. Learn. Kafka, RabbitMQ, events, producers, consumers, DLQ, idempotency, Saga basics. Practice. Build order created event flow. Week 4. Production readiness. Learn. Check. API gateway. Check. Circuit breaker. Observability. Check. Distributed tracing. Check. CI/CD. Check. Autoscaling. Check. Contract testing. Practice. Create production-ready microservices system design. Real-world project, cloud-native e-commerce microservices. Services. User service, product service, cart service, order service, payment service, inventory service, notification service. Infrastructure. Docker, Kubernetes, PostgreSQL, Redis, Kafka, API Gateway, Prometheus, Grafana, OpenTelemetry, GitHub Actions. Features. Cart search, cart management, order creation, product search, cart management, order creation, payment processing, inventory reservation, email notification, order tracking, admin dashboard. Final summary. Microservices system design is an essential skill for cloud-native software engineers. Important concepts include: check, service boundaries, business capabilities, database per service, API gateway, service discovery, REST, gRPC, event-driven communication, saga pattern, transactional outbox, idempotency, Kubernetes, observability, resilience, security, CI/CD. Backend developers already understand CAPS, APIs, databases, services, deployment, authentication, system design. This makes microservices easier to learn step by step. Key idea: cloud-native microservices help teams build scalable, resilient, independently deployable systems when the business and technical complexity justify distributed architecture.